Hello everyone, welcome back to my YouTube channel. My name is Gunashri R, pursuing my third semester BE in Electronics and Communication at Sri Venkateswara College of Engineering. Today I will be talking about the subject Electronic Principles and Circuits. The subject code is BEC 303 and my topic is Small Signal Analysis. What is small signal analysis? Small signal is the input voltage signal of BJT which is in low range such that the output varies linearly with the input. In other words, small signal analysis in BJT is a technique used to analyze the behavior of the transistor under small changes in input signal. It assumes that the transistor operates in its linear region where the output current is proportional to the input current. BJT with small AC input signal. Small AC signal refers to the input signal VBE whose magnitude is much smaller than thermal voltage VT. That is nothing but VBE is lesser than VT. Magnitude of the AC signal applied for amplification must be small so that the transistor operates in the linear region for the whole cycle of the input, which is called as linear amplifier. The second point is the transistor is never driven into saturation or cutoff region. On the other hand, if the input signal is too large, the fluctuations along the load line will drive the transistor into either saturation or cutoff. This clips the peaks of the input and the amplifier is no longer linear. Small signal analysis. Here we have a small signal equivalent circuit of a BJT where the emitter is connected to the ground. Emitter capacitor CE is a small signal short. RB is parallel with RPi and both are connected to the ground. RC is parallel with RL and both are connected to ground. Input voltage Vi of t appears across Rpi and is the same as VBE. The transistor is a transconductance device, so the input voltage VBE creates output current IC. To determine the small signal voltage gain, the formula is AV is equals to V out by V in, that is nothing but V naught by Vi, and AV is the voltage gain. The input is applied across the BE junction, so VBE is equals to Vi. Let's take this as equation number 2 and the voltage gain as equation number 1. The output is the collector current applied across the output resistance. So V0 is equals to minus IC R0. Here in the diagram, V0 is given by GM VBE. So when we replace it, it becomes minus GM VBE R0. Let's take this equation as equation number 3, where R0 is the total resistance seen by the collector. So R0 is equals to RC parallel to RL, which is nothing but RC into RL by RC plus RL. Let's take this equation as equation number 4. Now by substituting equation 4 and 2 into equation 3, we get V0 is equals to minus GM VI R0. By substituting R0 value, we get minus Vi into GM RC parallel to RL. The amplifier gain AV is equals to V0 by Vi is equals to minus GM RC parallel to RL is equals to minus GM R0. This is the gain for any common emitter amplifier. That is, the formula is AV is equals to minus GM R0. The negative sign indicates that the amplifier has inverting gain. Now let's calculate the output resistance and the gain for the given values of the circuit. For the output resistance, R0 is equals to RC parallel to RL, which is nothing but 820 ohm parallel to 1 kilo ohm. We get 451 ohms. And the gain is AV is equals to minus 188 millisecond into 451 ohms. We get minus 84.7. And the output for a 50 millivolt peak to peak 100 kilohertz input is the waveform below. Key parameters of small signal analysis. The key parameters in small signal models include transconductance, input and output resistances, and capacitances. These parameters determine a device's gain, impedance, and frequency response, shaping its performance in various applications like amplifiers, oscillators, and mixers. Small signal operation is a regime where the amplitude of the input signal to a circuit is sufficiently small that the circuit's behavior can be linearized. The linearization allows for easier analysis and design of circuits. Now let's see some of the characteristics of small signal analysis. Range of linearity. Ensure that the input signal stays within the linear region of the device or circuit. Exceeding this range can lead to distortion and nonlinear behavior. Distortion. Minimizing distortion by operating in the linear region. Common types of distortion include harmonic distortion, intermodulation distortion, and clipping. Gain stability. Ensure that the gain remains relatively constant over the desired operating range. Bandwidth. The range of frequencies over which the gain of the circuit remains relatively constant. Feedback. Be aware of feedback loops that can cause instability. Oscillations. Avoid oscillations by ensuring that the loop gain is less than 1 at all frequencies. Noise figure, a measure of the noise added by the circuit. Noise reduction, minimize noise by using low noise devices and proper circuit design techniques. Efficiency, minimize power consumption for battery powered or low power applications. Power supply rejection ratio PSRR, ensure that the circuit is not sensitive to power supply variations. Temperature coefficient, consider how the circuit's performance changes with temperature. And the last one is compensation. Use techniques to compensate for temperature related variations. By carefully considering these parameters and characteristics, we can design small signal circuits that meet our desired performance requirements and operate effectively in various applications. Thank you for watching.